38, hydrogen 36, oxygen 2. It shows to the right, see figure 1. To the left side of the molecule is polar or hydrophilic and is capable of hydrogen bonding with water. The rest of the molecule is hydrocarbon chain and is completely nonpolar or hydrophobic. We call the polar side the molecule, the head of the rest of the molecule the tail. If stearic acid molecules are placed on the water surface, the polar head molecule hydrogen bonds to the water molecules on the surface. The rest of the molecule, the non-polar tail, is not attached to the water, but rather is attracted to the tails of nearby stearic acid molecules. As a result, the molecules line up on the surface of the water with the polar heads on surface and non-polar tails sticking up away from the surface. See figure 2 below.
That's what's going to happen today in the lab. You're going to have a water surface on a plate, and you're going to place some talcum powder. We ran out of that, so we're going to use lycopodium powder. Lycopodium powder works better on acetone, but I'm not going to get out acetone because it's flammable. So we're just going to use the water surface, and the monolayer is actually the acid that's going to form a little circle when you put a drop on the water. You'll see that it's really pretty cool. Who wants to read? Points? All right, go ahead, Josh. Yeah.
If a small number of stearic acid molecules is placed on water, they cover the water with a layer 1 molecule thick. A monolayer is said to form. In this experiment, the thickness of a monolayer will be approximated to be the height of the stearic acid molecules, h, above the water level. This length is considerably shorter than the wavelength of visible light, so light striking the monolayer does not interact with it, and the layer is invisible to the eye. However, once enough additional molecules are added, they begin to pile up on top of one another, and the thicker part of the layer becomes visible.
Okay, very good. All right, so we're going to solve for H today in the lab, as you see up here on the board. Now, you're going to need to copy this down, measurements, and then do your data.
Which one is this, Stearic?
Huh? No. The one you just wrote down, obviously.
No, that's not.
Okay, the powder is over
Because I was trying not to.
right there. We've got some over there.
Y'all need platonic.
Okay, which one are you doing now?
Layering it. I have it right here.
Read and measure.
Lily, get the measurement.
Oh, that's amazing.
It looks like 9 centimeters.
Brandon, keep your goggles down.
I forgot. Okay, the one with an S.
That one. Which one are you doing now?
Doing it. Hey.
With a sorbic.
Are you ready? It's about like one.
Yelling.
Silver.
How do we get volume of drops and stuff like that?
Do your
Just asking.
Do like all of them
diameter first. One step at a time.
That's acid. We need the other one.
Okay.
Yeah, you don't want to move it once you place the talcum powder on there.
Gotcha.
Yeah.
No, you want it to be subtle.
Okay, what is...
Yeah, that's 2.5 or 6.
Talcum.
I don't know, I can't read the area and density will lead to an approximation of molecular size.
I like that.
Hey, that was me too.
So now can we just do another area?
Yeah.
Random Acts of Comedy on YouTube, everybody.
Measure it.
Measure it. I poured it.
You pour that?
Okay. See, they do
So have you measured those yet?
Not yet.
Well, get the ruler.
Get the ruler and measure it.
I will, okay?
God.
Be patient, Jacob.
Get this on video.
It's
Fight
about
in school.
2.5. Is this garlic powder?
No, that is like a podium powder.
Crap, I need to. Stearic acid is allowed to spread out until it's monomolecular thickness. Then calculations based on area and density will lead to an approximation of nuclear size.
Okay, very good. Now, Cameron, in this lab today, how many carboxylic acids are you going to be testing? Raise your hand. How many carboxylic acids are you going to be testing today? Raise your hand. 5. Very good. Naomi, Naomi counted them. They're right here. So you're going to test 5 different things, Josh. When you get over in the lab, you don't know what you're doing. Don't ask me. There are 5. The first one is sorbic, lauric, palmitic, stearic, and archimitic. So these are carboxylic acids. There are 5 of them. They are labeled in the lab. Is everybody clear? All right, so what you're going to do, on the back side there's a data table, and I'm videoing this because the data table is not very clear about what they want where. This right here is going to be continued all the way down. It's kind of like showing your work. That wasn't very clear to me first period. So over here you're going to write down your 5 acids. The diameter, when you place a drop in the circle where the water is, it's going to create a diameter, and you're going to measure that. And this is the radius, which is, raise your hand. Right, it's half the diameter. Now the drops, I had to go on the internet to find these. I found sorbic to be 20 drops as a milliliter, and I found stearic to be 64. I calculated the rest. That is, I took out a graduated cylinder and I put 42 drops in there to get 1 milliliter. Now I didn't have you do that because that's a waste of a lot of resources and I didn't want to do that. So you're going to write these values down. I calculated those. Don't want to lose those. I'll do that again. Now this part right here, the first one is done for you. If you look at the first side of the sheet where it says 112 times 0.05, everybody see that? This value stays the same all the way down. See, I wrote it twice, so it'd be 3, 4, 5. This concentration stays the same. They're all the acids have the same molar concentration. The densities will change. This is the density, and this is the molecular weight. See mole weight? That can be found on that data table. See the data table? So right underneath 112, you see 200. So 200 goes there, and then 0.88 goes here. Now when you do your math, it goes in the next column. This is the next column is where the math goes, right? Now here, you have to divide that by 20 because they want to know per drop. See, it says volume per drop. So you have 20 drops as a milliliter, right? And you're only putting 1 drop on the plate. So you're going to divide that by 20. That answer goes here. Now the last one, you're going to solve for the height. You take this value, that goes in the numerator. Now in the denominator you have pi r squared. So you've got your radius over here, and then you just square it, and you can solve for the height, right? So a similar lab can be done to calculate Avogadro's number, which is the mole. I passed that other lab out to you. It's very similar. I like this one a little bit better than the Avogadro one that I'm showing you here. I do like this one because the diagram is better, the picture is, right? But the data table on this one is not as good. So if you look at this, right? They don't really have any data table there. They just have a bunch of formulas. Whereas this sheet has a really good data table. So I kind of gave you both to kind of give you a visual of what you're actually doing. The objective of this can be found at the bottom of this page here, where it says actually what is really being estimated here is not the cross-sectional size of the molecule, but rather the cross-sectional space per molecule. So you could say the objective is to determine the cross-sectional space per molecule. That's what we're trying to do. That's the purpose. Naomi. The purpose is to determine the cross-sectional space of a molecule. Now what are you going to do in the lab today? You're going to test 5 different acids. You have a plate of water, some lycopodium powder, a drop on it. It's going to create a circle, and you want to measure that circle. So doing the lab is very quick. You can probably do this lab in like 3 minutes. It's the math that's going to take you a little bit more time to do. So when we come in tomorrow, I'll probably give you like a graph paper and we'll graph this just to see what it looks like, and then we'll turn it in.
I always like write something, but like, can you explain the weight and the
Yeah, the weight comes from your data table. So if you look right here, you see how it says 112? That number will change, it'll go to 200.
Okay.
And then 0.94 will change to 0.88.
Should we write these down?
Right, so the next lauric acid is going to be 0.005, and then it'll be 200 and 0.88. So these two numbers will change. These will, this stays the same, these two change for this acid. So there's a kind of a pattern there. Any other questions? Yes, you only have to turn in one per group. Who got the roses?
Tamara.
Oh, is it her birthday?
It's from me.
No, it's 7 months before her boyfriend.
It's from me.
So nice.
It's from Vance.
Be nice.
Tamara needs some explanation on like how to do the calculations.
Okay. So calculations.
I have no idea.
Good. If you have a question, ask. Nice job.
It didn't work that well, Mr.
You're going to want to measure quickly though, because it's going to want to contract, and that's going to affect your monolayer.
Should I get a different spot?
You can do a different spot. I'd go over here. But be ready to measure it though.
Easier than I water.
I'm scared of it.
Okay, we ain't got a ruler. I do. Stop.
It's not really.
Pretty cool, isn't it? It wasn't a perfect circle, but you know.
Metric or inches?
Are you doing it? Palmatic?
Alright, so we're gonna have to do this.
How you say that?
Carboxylic?
Carboxylic acid is allowed to spread out until it's monomolecular in thickness. Then computations based on area and density will lead to an approximation of molecular size.
You're very good.
See why it takes you forever.
Nice. Can you measure quickly?
Measure quickly?
Yeah, because it's going to shrink on you.
Just like this.